Here is another way to model a double pendulum. Okay, so if you're just getting here, I already did this problem. So let's start off with the beginning. What's a double pendulum? So a pendulum would be just a mass connected by a string to a pivot point, and it can swing back and forth. It's a surprisingly complicated problem, even though it's used in a lot of places. It's not easy. Now, a double pendulum is the same thing, except that you have another pendulum on the end of that other mass. And this is confined to move in just 2 dimensions. So you can build them with some bearings and stuff like that, so it stays in 2 dimensions. It makes a great chaotic system. They're really fun to play with, but to model, it's not so trivial. So how did I model this before? And you can check out the video. The idea is to define the system based on 2 coordinates, theta 1 and theta 2, and then I can find the equation of motion using Lagrangian. So the Lagrangian says that the Lagrangian is kinetic energy minus potential. So you have to find the kinetic and potential energy of these in terms of theta 1 and theta 2 and their derivatives with time, and that's not so trivial. Okay, but then it gets even worse because I have to use the Euler-Lagrange equation, partial of L with respect to theta 1 minus d dt partial of L with respect to theta 1 dot. That's the time derivative of theta 1 is 0, and do the same thing for theta 2. Let me just show you where I've already done this video, and you can go look at all the details. But this is what you would have to do because the kinetic energy in polar coordinates is not trivial, especially for this one, since this point moves and theta 2 it moves too. So you write the kinetic energy in terms of Cartesian coordinates, and then you find the relationship between Cartesian coordinates and your generalized coordinates theta, and then you can take the derivatives of these x1 and x2, y1, y2, plug them in here, and same thing for the potential energy, and you can get L in terms of theta 1 and theta 2, and then you take the 2, I don't have L, but then you take the 2 derivatives, the 2 Euler-Lagrange equation gives you these 2 equations. It's not so trivial. What's that? Is that it? No, that might just be no, I think that's it. That's just one of them, I think. I don't know, it doesn't matter. You can see the whole video. It's messy. I'll be honest with you, it's messy. And let's think why we have to do that. The problem is that these strings are forces of constraint, and Lagrangian works really well with force of constraint because we don't really care about actual variables. We can define variables that are defined in the system of constraints. So theta 2 just moves back and forth here, and theta 1 there, and I can get everything in terms of theta 1 and theta 2. Those are the generalized coordinates. It just makes more sense. So the problem is these forces of constraint. The tension right here, yes, you technically could calculate the tension, but the tension in this string right here depends on the value of mass m2, the gravitational force, the angle, and the velocity too. Because if this is moving down if it's moving in a circle, then that tension makes it move in a circle. But it's not even moving in a clear circle because this piece is moving in a circle. If you just do that one simple pendulum, it's not terrible. But when you add this other one there, it's terrible. Okay. Forces of constraint are just really hard to deal with. They change direction, they change magnitude, and we don't even know what that is. So if I do know the force, if I have an equation for that force, I can actually model this with the normal Euler numerical calculation. So here's how it works. Suppose I have the force on mass 2. I'll call it F2. F2 equals stuff. And that's a vector. And so stuff is something I calculate. I know it. I know the force. It's gravitational force plus whatever. But I know a value for it, even an expression in some way. Then I can say that's equal to, according to the momentum principle, delta P over delta T. So over some short time interval, this is going to be the change in momentum. You could also say acceleration, but mass times acceleration doesn't really matter. So you could use velocity. I'm going to use momentum. Change in momentum or the change in time. And if I assume that this is P2, if I assume that this is a short time interval, then the force is constant. I can write this as P22 minus P21 over delta T. So P22 is the momentum at the end of the time interval. P21 is the momentum at the beginning of the time interval. And so I can solve this for P22. P22 equals P21 plus F2, and that's force on 2, delta T. So if I know the momentum at the beginning, if I calculate the force with the time interval, I can find the momentum at the end. Then I can do the same thing for position. So it's called the final position of mass 2 is R22. So I can say R22 is going to be equal to R21, the position at the beginning of the time interval, plus P22, the momentum at the end, divided by the mass 2 times delta T. That's the velocity. So I can update the momentum, I can update the velocity. But this all hinges on one important point. I need to calculate that force. And I can do that because I'm going to take that string and replace it with a spring. So instead, I'm going to actually have this system. Here's the spring. And then I'm going to draw it this way. I should have. Poor planning. So there's M1, M2, and now I have 2 springs. And I can calculate the force due to a spring at each instant. It depends on where it is in relationship to the attachment point. And I can do that. So I can break this into short time steps, calculate the net force on M1 and M2 by using these springs, use that to put the momentum of the 2 masses, update the position of the 2 masses, and do it all over again. And let's see if we can get something that looks like a double pendulum. It's not technically a double pendulum, but if this is a stiff enough spring, it's going to act like a double pendulum. I'm not sure if it will give me the exact same thing, but maybe we could test that out. So let's look at springs. Now, we have to use a better model for a spring. So suppose I have some pivot point here, and then I have some mass down here, M1, and then here's my spring. And I missed. Look at that. I missed. Okay. There's a couple things that I can calculate. The first is I'm going to call this L. I would normally call it L0. I'm going to call this R10. R10 is the unstretched length of the spring. That's how long it is if it's not stretched. Because the spring force depends on how much it's either stretched or compressed. But I need to know how much it is, how long it is when it's not stretched or compressed. Okay, so then I can call this R1, which I think I used somewhere else. So I'm going to call this, let's call this R1, is going to be the vector from here to there. From the pivot point to the mass. And so I can find that. If I know the location of these 2 things, then it's just going to be the vector difference between those 2. And then I need to know the spring constant. And with that, I can write the spring force, F, I'll call it S1, spring 1, is going to be equal to negative K times the magnitude of R1 minus R10, right? I have to take the magnitude because it's a scalar. That's a scalar, that's a scalar. But I need a vector force, so I'm going to multiply this by R1 hat, the unit vector in the direction of R1. Now let me just check. So let's suppose that this goes 2, it's longer, then the force should be pulling in the opposite direction of R1. So this would be greater than that, so this would be a positive number. I'd multiply by R1 and then have a negative sign. So K is the spring constant, R1 is the vector, R10 is the unstretched length, and I can calculate that. Okay, let's just do this with 1 spring, and then I'll come back and I'll do it with 2 springs. So let me just look. I'm looking at my old program over here. I had R10, which I just called R1, is equal to 0.1. Theta 1 is equal to 81 pi. Why did I write it like that? Pi over 180. Gosh. Mass M1 is equal to 0.1. Okay, that's fine. So I'm going to make a mass and just one single thing and make a pendulum. And then when that's working, I'm going to go back and add it another mass at the end, and we'll do it that way. Okay, so let's jump over to GlowScript v Python. I'm trying to think if, I'll include a link to my other 2 videos in this. The first one I derived the differential equation of motion. The second one I model it in Python. But I'll provide a link also to some numerical stuff and some spring stuff in case you want to look at that. But let's jump over to Python. I'm going to be using GlowScript VPython. So this is GlowScript VPython. It's actually, I'm sorry, now it's called Web VPython. This is an implementation of Python that has all the visual stuff in it in a web page. And I'm going to give you the link to this code. I like this particular place because this is Trinket, because you can edit the code and run it without even logging in. So I can share it very easily for you. So let's just make this a little bit bigger. That may be big enough. Okay, now I need some variables. I'm going to say g equals vector 0, negative 9.8, 0. Now, but in the past I used g as 9.8. But now I'm going to use the vector g because I'm doing this as vector forces. So I actually need the vector g. I'm going to call it a vector g. Let's say R10, I called it that before, 0.1, M1 equals 0.1. What else do I need? Oh, theta 1. Theta 1 equals 81 times pi divided by 180. And this is actually pretty good because this would not work with your normal pendulum equation, right? Because the angle's too big. Okay, let's just go ahead and jump into this. The first thing I'm going to do is to make a pivot point. This is the point where the spring attaches to. Now, I don't want to start this at the origin just because if I shift it up, it looks a little bit better. So I'm going to say pivot equals an object called a sphere. The position is actually going to be equal to, I'm going to shift it up R10 over 2. So it's going to be 0, R10 over 2, 0. So it's shifted up. Now I need to give it a size. Let's just give it a size of R10 divided by 20. I don't know. And let's run that. And there's my pivot point. Everyone's happy. Yay. Okay. Spring double pendulum. I need to save it. Okay, now I'm going to make mass 1. This is called M1 lowercase as sphere. The position, okay. Now, where is this going to be? It's going to be relative to the pivot. And then I'm going to use my conversion, just like I did before. It's going to be R1 cosine theta. No, R1 sine theta in the x direction and negative R1 cosine theta in the y direction. So the position is going to be the position of the pivot, pivot.pos, plus R10 times vector sine theta 1 negative cosine theta 1 0. And now I need to give it a size. Let's make it a little bit bigger. Radius equals R10 divided by 15. Color is yellow. Make trail equals true and run it. Okay, that seems fine. Now I need something else. I need the spring. So I'm going to call that S1. It's an object of type cylinder. Its position. So a cylinder has two main properties. It has more than those, but one is the position, which is the location of one end of the cylinder, and the other is axis, which is a vector from the beginning to the end of that. So the position is going to be equal to pivot.pos. It's going to be mounted at the pivot point, pivot.pos. The axis is going to be equal to m1.pos minus pivot.pos. Radius is going to be equal to R10 divided by, let's say, 30, and let's leave it as gray. There. That looks pretty good. Okay. Now I need a couple other parameters here. I'm going to need the value of K. Let's put it at 50. I'm just picking 50 newtons per meter. I need the initial momentum for mass 1. So M1 is going to be equal to, no, M1.P is vector 0, 0, 0. Okay. I need T equals 0, dt equals 0.001. And I think that's good. While t is less than 5, rate 1,000. So rate 1,000 says don't do more than 1,000 calculations per second. And that will make this run in real time, since I have a time step of 1/1000th of a second. Okay, so the first thing I'm going to do, I want to calculate that force. But before I do that, I need to calculate this vector r1. So I'm going to call this r1 is going to be vector. No, it's not. It's going to be m1.pos minus pivot.pos. That's it, right? Because that's the vector from the pivot point to mass 1. Now let's calculate fs1. It's going to be equal to negative k times mag r1. This is exactly what I had in my equation, right? Mag r1 minus r1. R10 times norm r1. Now I can calculate the total force. I'll call it F1. It's going to be Fs1 plus M1 times G. Now, that's plus, right? It's plus because G has a negative y component, but I'm not subtracting that whole thing. Those are two vectors. I'm adding two vectors. I get a vector equation. Now I know the net force. I can update the momentum. M1.P equals M1.P plus F1 times dt. Now I can update the position. M1.pos equals M1.pos plus M1.p times dt divided by M1. Okay, I need to update time. T equals T plus dt. Actually, I need to also update the spring, right? The pivot points is not going to move. So the position isn't going to change, but the axis does change. So I can say S1.axis equals R1. That's it. I think this should work. Okay, so you're thinking, that don't look like a pendulum. Okay, I can fix this. There's two ways I can fix this. It does look like a pendulum, number one. Number two, I could increase the spring constant, right? And that would fix almost everything. But I want to show you one other way, because I want to make this as best as I can. When I start this, that spring, right when it lets go, the length gets longer because it's falling and stretching the spring. But what I want to do is pre-stretch the spring. I want to pre-stretch the spring so that when I release it, it starts with the correct. It doesn't stretch right away. It stretches a little bit at the end, but not the other way. So let me switch over here to the paper and show you how we're going to pre-stretch the spring. Okay, so let's suppose this is theta 1. And I have two forces acting on this. I have the downward gravitational force, mg, and then I'll just call that Fs. What did I call it before? Fs1. What I want is for the net force in this direction to be 0. So right when it lets go, it will not stretch the spring right away. So if that's the case, I can say, what are these forces? Well, I have a part of the gravitational force. I have mg cosine theta 1, and that's the scalar value of g, should be equal to the k times S1, where S1 is the stretch, right? I can write the spring constant as, the spring force is k times the stretch. And so I can want to solve for S1. That's easy. S1 is mg cosine theta 1 over k. Now, I can say S1, well, I can say R1 to begin with is going to be R10 plus S1. So that's the initial stretch. That'll give me the initial stretch. So let's put that in my program and see what happens. Okay, so up here when I made it, instead of just saying R10, I'm going to say S1 equals M1 times mag G, right? I can't use the vector G, times cosine, is that right, cosine? Yeah, cosine theta 1 divided by k. And that's not going to work because I put k down here. So let's just move this up here. Okay. That's S1. That's how much it's... I called that the wrong thing. S1. All right, because I have S1 is actually the spring. I can't use it twice. I could, but I don't want to. So then I'm going to have, instead of just R10, I'm going to have R10 plus SS1. So it's going to be a little bit longer. It's going to start off longer. It's going to be pre-stretched. And let's see what happens if I just make that one simple change. So it's not swinging back and forth as, it's not wiggling as much. If I increase this to, let's say, 100 for the spring constant, it still does it. Let's go even higher. We can go higher, 1,000. There. That looks like a pendulum to me. It still is shaking up and down, okay, but it's mostly a pendulum. Okay, so now we're going to add our second mass. We're going to do the exact same thing. Right, we're going to have theta 2, we're going to have mass 2, we're going to have another spring. Really the only difference here is that for that second spring, it's going to be attached to mass 1, not to the pivot point. Okay, so I think we can go ahead and just add that in there. We don't need to go back to the paper. Let's just do it. Let's get theta 2. I'm going to look at my program I did last time. I had theta 2 is 75. I'm going to use that same value. Theta 2 is equal to 75 times pi divided by 180. I'm going to have the same. You could have different spring constants for the two things. I'm just going to leave them the same. So now I can calculate. Oh, I do need to go paper because the stretch is going to be different, right? Now mass 1 is going to have a different stretch. So let's go ahead and calculate that. Let's look at that on paper. Okay, so suppose it gets released from rest. So there's my pivot. There's mass 1, and there's mass 2. So let's first calculate the stretch for this one, SS2. So I have two forces, the downward gravitational force M2G, and then we'll call that FS2. And so that's theta 2. That's theta 2. So this looks just like before. SS2 equals M2G cosine theta 2 over K. That's just like before. Now for mass 1, we actually have three forces acting on it. So here is this. This is going to be theta 1. And I want the forces in the theta 1 direction to be constant. So I have, I have FS1. I have M1G. And then I have that other force right there, FS2. So I need, in the theta direction, I have two forces pulling this way and one that way. So I have FS1, which is going to be K times SS1. That's the spring force. And now in the other direction, I have M1G cosine theta 1. And then I have this component. So this is going to be equal to, this angle right here is going to be equal to theta 2 minus theta 1. So it's going to be plus FS2 times cosine theta 2 minus theta 1. This might not work. And then I can put in for FS2, I can put in SS2 times K. So this means I have K SS1 equals M1G cosine theta 1 plus K SS2 cosine theta 2 minus theta 1. So SS1, I just divided both sides by K. Okay, let's try that. This might be a disaster. That's fine. We don't have to pre-stretch them. I was just trying to be cool. So I'm going to actually call this SS2. And this is going to be M2 G cosine theta 2. And then I'm going to say SS1. I'm just typing in the equation. Just wrote down M1 times mag G times cosine theta 1. All of this in parentheses. Plus K times SS2, which I just calculated, times cosine theta 2 minus theta 1, close parentheses divided by k. Okay, let's just see if that works. Okay, so there's my S1 is already, it's all set. Okay, I just need to make S2. So let's say M2 is sphere. Position is going to be equal to M1.pos. I'm not going to add it to the pivot. I'm going to add it to the other one. So M1.pos plus, oh, I need this R20 equals 0.1. M2 equals 0.1 there. Plus R20 plus SS2 times vector sine theta 2 minus cosine theta 2 0. No, I just did O twice. Wow. Okay. And then I'm going to put same radius. Radius equals R20 divided by 15. Color is color.yellow. Make trail equals true. Now up here, I'm going to turn this one to false. I only want one trail. Okay. Let's just run that and see what happens. See, good thing I ran it. Can't find, aha, I can't spell. Fiat, theta. Okay. It won't run correctly, but yeah, it's just sitting there. Okay, that's fine. Okay, now I need a second spring. Let's do this. M2.p equals vector 0, 0, 0. And then I'm going to put, it's out of order, S2 equals cylinder. Position equals M1.pos. Axis equals M2.pos minus M1.pos. And then the radius is, what did I use before? R20 divided by 30. Okay, I think that's fine. Let's just jump down here and do everything else. Let's see if this whole thing works. R2 equals M2.pos minus M1.pos. FS1, that didn't change. FS2 is going to be equal to negative K times mag R2 minus R20 times norm R2. Okay, now F1 is going to be equal to the spring plus gravity minus FS2, right? Because if FS2 is the force on mass 2, then that pulls on the opposite direction for mass 1. F2 is going to be FS2 plus M2 times G. Okay, so now I don't need to change this line updating mass 1 momentum. I don't need to change that one, don't need to change that. Let's do the same thing for mass 2. So mass 2, M2.p equals M2.p plus F2 times dt. M2.pos equals M2.pos plus M2.p times dt divided by M2. I need to update the spring S2. Now that one I need to update both the axis and the position. So S2.position is M1.pos because M1 moved. And then S2.axis equals S equals R2. I think that's right. Okay, I'm just going to run it. Okay, so you'll notice that there's some shaking, but oh, that does look very shaky, especially for that top one. We could plot and calculate the total energy, but you'd have to do the total spring potential energy, kinetic energy, and all that stuff. It actually wouldn't be too hard to do. But I'm positive energy is conserved. So you can do that as a homework. Let's just increase the spring constant to 5,000 and see what happens. See if it looks a bit different. Okay, I think it's okay. Let's change these initial angles. Let's change this one to 15. I want to get some like chaotic types. There we go. 15 and 85 changes to 35. It does seem like it's oscillating quite a bit. I think I need to increase that spring constant to even higher. Let's just do something crazy, 20,000. Now, with such a high spring constant, I probably need to decrease my time interval. So I'm going to do that. And you'll see the problem doing it this way. I really need a lot more calculations in order to model it, but I did less work setting it up. So it's always a give and take in these kind of situations. I think this is okay. Now, I have a couple homework assignments for you. Number one is to model this. Take this code. Take the code for the Lagrangian model and model them both with the same initial conditions and the same program and see how much they diverge. That would be kind of fun, right? And see how close you can get the two things to act. If you want a real double pendulum, you have to go with the Lagrangian. But this one, if you want a quick double pendulum, this would work too. So just another example of using springs in place of forces of constraint. So there you go. Okay, like I said, I'll include the other videos down below. This is part of, I think, put it in a playlist. So you got those. Hopefully that's helpful. I'll talk to you later.